So that's the derivation of electromagnetic wave equation for light. I think there's one feature that I kind of skipped over, which is probably worth not skipping over. Let's see, how do I get to that? I think the best way to get to it is through this expression here. This expression, which we kind of used without looking into too much detail of it. So let me point out the part that I want you to look at and see. So let me write down the right-hand side first, since that's something I feel more comfortable with. I guess I can actually erase all of this. Don't need any of this. Maybe I might have needed some of it, but that's okay. I kind of remember the simplifying conditions I've made. So let me write this down first. So the right-hand side is mu naught, epsilon naught. And I'm going to write down electric field in the form, simplified form that we have chosen. So the time derivative of y component of the electric field, which only depends on position x. Right? That's the right-hand side here. And what I want to do is I want to expand out the left-hand side so that you can say something about the relationship between magnetic field and an electric field in the electromagnetic wave. So the left-hand side, it's going to look complicated. So let me write all this out. So let's see, do I want to? I wonder if I can simplify some things. I think I can make one simplification so that I don't have to write down everything. So we are doing the same thing, right? So we are looking at a charge that's oscillating very far away, so that here it looks like a plane wave, which means we can say that the magnetic field as well as electric field is only going to be function of x, not function of y or z. Good? So I'm going through the same step that I did before with this. So starting from this divergence for magnetic field, what we can say is, when we say the divergence of magnetic field, or writing it out in terms of components, is the x derivative of x component, which is only going to be function of x, plus the y derivative of the y component, which is only going to be function of x, plus the z derivative of the z component, which is only going to be function of x, and all of that is equal to 0. Then you see the same thing you saw last time. We end up saying that, well, this is 0 because it doesn't depend on z. This is also 0 because it doesn't depend on y, only depends on x. Since this entire thing is 0, that means this also must be equal to 0. So the magnetic field also has no oscillating x component. So my magnetic field as a vector might have a y component, which will depend on x. And it might have z component, which will depend on x. But that's it. No x component. So both electric and magnetic fields are transverse in an electromagnetic wave. And what I wanted to show here was the direction of magnetic field, given that this is the propagation direction. Propagation direction. That's the direction that wave is moving in the sense that waves move. And this is the direction of electric field. I want to see, okay, what's going to be the direction of magnetic field? So let's write it out. Out of this Ampere's law equation, I wrote down the right-hand side. Let's write down the left-hand side with this simplifying knowledge in mind. So I'm looking at this here. I'm taking the curl of that. So let's just write it down term by term. So when I take the curl, it's going to potentially have x component, y component, and g component. Let's see which components don't go to 0. So I'm gonna, simply stare at some things to argue that they are 0 without actually writing it down. So as I take the curl of this, I refer to this expression here. For the x component, I'm taking the curl of g component with respect to y. Well, that's a 0. I'm taking curl of the y component with respect to z. Well, that's also 0. So I can say x component of this is 0. Kind of good. And I guess when you actually add, well, let me just continue on without spoilers. Okay, the y component. So the so x well, it has no x component, so that's a 0. G component with respect to x. All right, so that's not going to be 0. So I have to write down this is. Wait, there's minus. I feel like I'm missing something, but whatever. I'll keep going. Minus. I feel like I'm missing something. Not making a mistake, right? It's the minus. Oh, no, I'm doing this one. So it is just curl. Well, let me write it down. So I'm doing the y component, the second term. So the derivative of the g component with respect to x. So minus derivative with respect to x, bg. Feel like that minus sign doesn't belong there, but we'll see. Yeah, I think I might know why that's there. I'll have to reason that through. G component. Well, let's see. It says so y component with respect to x. That's not 0. That is it. So I have to write that down. Y component derivative with respect to x. Derivative with respect to x of the y component of magnetic field. It's there. I have to write it down. X component, okay, that's a 0. So that's 0. So this is what I end up. And here's the reason that you might hesitate as you write down this term. Can my right-hand side have any g component? Can my right-hand side have any g component? Looking at this equation, am I allowed to have a non-zero g component? Why not? Yeah, left-hand side only has y component. But this is telling me I have a g component. So what does that mean? Well, there's really only one solution. This offending term must be 0. Right? That's the only way I can make this equation work. Or, I guess this could be a constant term. So the oscillation term is 0. So here, with the magnetic field, I didn't start by assuming that this is going to be 0. I tried to include all the terms that might possibly appear. But because of our earlier simplification, saying that electric field is along the y direction, we had to say, well, the y component can exist. My magnetic field can only have g component, no y component. So by the way, a lot of lower division physics textbooks will give this fact to you as a fact that you might have to memorize. I guess you should actually memorize. But what I want to show you here is these facts that you will see cited in a lower division physics textbook. It's something you can derive from Maxwell's equations. It's something that you can theoretically figure out. And what this means is this. So, well, I'll go through the argument, and when I do it, what you'll find is that magnetic field actually points along the z direction. That's the direction of magnetic field. So, so this is always going to be arrangement of electric, magnetic field, and propagation direction. It'll always be the electric field is perpendicular to magnetic field. And both of them are perpendicular to the propagation direction. And in fact, they are arranged in such a way, when you do E cross B, then the cross product points in the direction of propagation direction. So and that's what this equation is showing. Because once you said electric field points in the y direction, then magnetic field along that direction has to be 0. So it can only have the z direction. And I guess showing that it's pointing in positive direction, even though there's this minus sign, I don't know if I want to go through that. Yeah, I should go through that detailed argument. It comes down to looking at sort of how these two are related. I guess simplest way to show is this. Let me write down a form for electric field and magnetic field as a sort of periodic traveling wave solution thing. So I might say electric field, the magnitude is amplitude times cosine of kx minus omega t. Do people remember this way of writing traveling wave? Yes, wave number times x minus omega t. This represents wave traveling to the right, or wave traveling in the plus x direction. Yes? And this is what I'm going to assert. I'm going to assert that the magnetic field, which apparently points in the z direction, it also takes this form. This portion looks exactly the same, cosine of kx minus omega t. And there's some amplitude of b naught, which actually I'm trying to figure out, like how that relates to electric field. So let me plug in these two gases into this equation, and let's see what we end up with. So when I plug them in, this is what you end up with. The left-hand side will look like mu naught epsilon naught, mu naught epsilon naught. I'm going to just skip the y hat because I know I'm dealing with the y component. I'm taking the time derivative of electric field. So I'll get a factor of minus omega out, but cosine, so it'll be plus. So it'll be, the derivative will be plus omega E naught sine of kx minus omega t. Everyone okay with this as the derivative, time derivative of this function here? Okay, so I want to say that is equal to this term here minus of the position derivative here. Well, minus and then minus sign, so minus also cancel out. And I'll get plus, and the k factor comes out, k times b naught sine of kx minus omega t. Okay. So let me see what the relationship between b naught and e naught is. So sine of kx minus omega t cancels out. It goes disappears, well, cancels out from both sides. So let me just solve it for b naught. So when I solve it for b naught, this is what I end up with. The amplitude of the magnetic field oscillation is equal to amplitude of the electric field oscillation times mu naught epsilon naught, and then omega over k. Let's rewrite these two in terms of speed of light. We know what mu naught epsilon naught was, right? 1 over v squared, or 1 over speed of light. So that's that. So this is 1 over speed of light squared. What's omega over k? Do people remember what that was? So k is related to wavelength. The wave number k is related to wavelength by 2 pi over lambda. And if you want me to write it down, omega is related to frequency by 2 pi times frequency. So what's omega over k? Can you say it louder?
Would it just be off of the Oh, sorry. No.
Do the algebra. You can write it down. I mean, it might not be easy to just do that in your head. Lambda, so wavelength times frequency. What is that physically equal to? Wave speed. Yeah, so this omega over k, I mean, it's an expression that's good to memorize, but in case you didn't, you can work through this and get that this is equal to speed of the wave, or in this case, c. So actually, so one factor of this cancels out one factor of this, and you get this rather simple expression, which you can take as being true of any magnetic field in an electromagnetic wave. The amplitude of the magnetic field is the amplitude of electric field divided by c. It's a relationship that you find between a magnetic field and an electric field in an electromagnetic wave. It's I think actually that was one of the multiple choice questions I was asking in the one of the final exam questions, but this is a useful factor to memorize for a number of reasons. One of them being, this tells you how the units of electric field and magnetic field are related. Like, you wouldn't guess this from the beginning, but what it's telling you is that unit of magnetic field, Tesla, is unit of electric field, volt per meter, divided by meters per second. So Tesla is volt times a second per meter squared. I mean, that's a kind of relationship that you wouldn't bother memorizing. But if you know this relationship, then that's something that you can get at. And that actually makes sense with this formula here, because speed times magnetic field must have same unit as electric field. Right? All right, so that's the derivation of electromagnetic wave and some of the very basic properties of electromagnetic wave. The relationship between the direction of electric field and the propagation direction. It's a transverse wave. And the relationship between electric field and the magnetic field.